Okay guys, in this video segment we're going to talk about hydrates and how they work, electrical conduction, like dissolves like, and also a little bit about the speed of the dissolving process. Okay, so we've talked hydrates before in this this year. We named hydrates like cobalt chloride, hexahydrate, or copper sulfate, pentahydrate, where we're attaching 6 waters or attaching 5 waters to the end of an ionic compound. What we haven't done is talk a little bit more detail on what hydrates actually are and some of the terminology that we use with them in solutions. Basically what a hydrate is, it's an ionic crystal that just has water embedded in it. So the water helps stabilize the crystal. It makes it a little bit more stable form for the crystal to form under. So it's preferred for the ionic compound to actually have the water with it. Now when we're working with hydrates, we have some terms that we work with. So the first one is hygroscopic. Hygroscopic just tells us that the compound is able to take water out of the air and attach it to the ionic crystal to form the hydrate. Okay, so not all compounds can do this, but if you're hygroscopic, what that means is if you leave a compound sit in open air, over time it will slowly absorb moisture and actually embed that into its crystal lattice. Now if you use this process or these properties of being hygroscopic for a purpose as a drying agent, then we give it a different term. We call that a desiccant. Okay? Now desiccants are used in chemical labs where we actually store things around desiccants so that they don't absorb moisture, but it also is used in industry and manufacturing, in particular silica gel. Silica gel is those little packets you find inside your purses or your new pair of running shoes, or maybe like a dress pair of pants, or in beef jerky packets that has these things in them. What the silica gel does, it acts as a desiccant, or basically it absorbs any excess moisture in these products. That allows people to manufacture them and ship them around the world and ship them in and out of humid countries where normally humidity might ruin these packages or ruin these products. So packaging them in silica gel helps preserve them. Also, you might see silica gel packets, bigger ones, in safes, gun safes, those kind of areas, maybe someplace you have to store important documents that are sealed because it helps keep any moisture, humidity out of those documents also. Now, if you have a hygroscopic compound that is so good at doing its job, you actually could get something called deliquescent. Now, deliquescent compounds, they're just hygroscopic, but they dissolve so much water that instead of adding those to the crystal lattice, they actually dissolve themselves. So think about something that keeps pulling water in, pulling water and pulling water in until the point it actually generates a very concentrated solution of itself. Okay? So that's a deliquescent compound. Now some of your more strong bases are very commonly do this. So sodium hydroxide, potassium hydroxide are things that are deliquescent. Now if you flip the switch and we go to the other side of the fact, if you have something that effloresces, that's losing water from a hydrate. So some hydrates are formed initially, and then if you leave them sit out over time, they actually will effloresce, or they actually will lose their moisture and become an anhydrate. Another way of doing this is we actually can take a hydrate, heat it up under high heat, and force the water to leave and force that water to evaporate. When we do that, we actually can force an anhydrate. Now, an anhydrate is just basically a hydrate that somehow all the water has been removed, either through a natural process or forced to be done so in a lab setting. So anhydrates, another word for that is anhydrous. Okay, so if you see an anhydrate, it just means you had a hydrate that you took the water out of, and anhydrous means basically generically without water. You may have heard of something like anhydrous ammonia. Well, ammonia typically comes in a liquid form as a solution in water, but anhydrous ammonia comes with the water missing from that, and it's a fertilizer that a lot of farmers use, and they spread it on in its solid form on their fields. So those are your terms that we deal with when we talk about hydrates. Now here's a little video for you about this idea of a deliquescent compound, and actually you can see it happen.
Many chemical compounds have the ability to absorb water directly from the air and form stable hydrates. These compounds are known as hygroscopic. Some compounds are so hygroscopic that they will absorb enough moisture to dissolve themselves. Here, shown with time-lapse photography, sodium hydroxide pellets absorb moisture directly from the air. This process of self-dissolving is called deliquescence.
Alright, so the video stops there. If they allowed the video to keep running for a longer period of time, those actual droplets that look kind of like spongy at the end would have turned clear, and you would have had a clear solution of sodium hydroxide in there. So that is what kind of deliquescence does. Our next major topic within this video segment is the idea of what dissolves what. Okay, so if I have water, what can it dissolve? Can it dissolve everything or only certain chemicals? There's actually one simple rule we follow when determining if something is most likely going to be able to dissolve something. And that rule is like dissolves like. And in particular, the like dissolves like refers to polarity. So if you recall, we talked about polarity earlier this year. Remember, polar molecules have a partially negative side to them, have a partially positive side to them. They tend to be bent or pyramidal shaped structures, and they tend to have something that's more electronegative and something that's less electronegative within that covalent structure. Now, within like dissolves like, what we say is that if you're a polar substance or an ionic substance, you can dissolve something else that's polar or ionic. Okay? Now, water's polar, so water falls in this category. What happens is this: because water has a positive side and a negative side, it will attract other things with positive and negative sides to it. It also will repel things that don't have a positive or negative side to it because it can't attract those things. So what happens is it actually kind of pushes anything that's non-polar away from it and actually attracts things that are polar or ionic. Now, ionic is involved in this because ionic really is the same as polar. It's just an extreme case of that. One thing we do want to make sure is that when we look at for solubility, go back to that solubility chart in our periodic tables and check for solubility of ionic compounds. Because some ionic compounds, their crystal lattice is strong enough where even though they have the same like dissolves like, where they're both polar ionic, they still won't dissolve because the crystal lattice of that ionic compound is just too strong to allow the water molecules to separate that crystal apart. Now, if you're nonpolar, that doesn't mean you can't dissolve into anything. It just means that you have to dissolve into another nonpolar solvent. So if there's no polarity there, nonpolar things will dissolve into other nonpolar things. Okay. For example, like oils and greases, they would dissolve into like a gasoline or a hexane because they're both nonpolar. However, water won't dissolve into oil or oil into water or gasoline into water because gasoline and oils are nonpolar and water is a polar substance. Okay, so we normally can't have polar things binding with nonpolar things or nonpolar things with ionic things because of differences in those charges. However, there are products out there called emulsifiers and surfactants. Now, what an emulsifier does and a surfactant does, they basically provide a link between that polar and nonpolar substance. If you can imagine that emulsifier and surfactants are these really long chain carbons. So imagine 15, 20 chains of carbons in a big sequence in a long row. Now, all that carbon chain would be very nonpolar normally. However, on the end of it, they attach either an ionic substance or a very polar substance. So what you get is a very long molecule where one side is very polar and the other side is very nonpolar. So essentially, within one molecule, because of the distance that separates them, you get a nonpolar side and a polar side. Well, if you have a nonpolar side, that can attach to your oils, your greases, your grimes, that kind of stuff that are nonpolar. The polar side can attach to water. So what happens is things that are food products that you're trying to bind together, you can actually get them to bind together by using an emulsifier. If it's a non-food product, we use the term surfactant. They mean the same thing. Emulsifiers tend to be just your food things. Surfactants, probably the most common thing you'd think of would be soaps and detergents because they bind like your oils and dirts on the nonpolar side to water on the polar side and allow us to use water and soaps as a cleaning product. We have two videos down here that's going to allow you to kind of go through this idea of how surfactants work. The first one and the second one are similar, but they kind of provide a little bit different visual. So here we go.
Soap consists of compounds such as sodium stearate. The stearate ion has a long hydrocarbon end that is nonpolar and hydrophobic, and a carboxyl group end that is ionic and hydrophilic. In water, the stearate ions associate into micelles, in which the hydrocarbon ends point inward toward one another.
So if you look, here is your polar end, and these are all negatively kind of charged, and these long nonpolar carbon chains sit on the inside. So these nonpolar molecule parts would actually group up together, kind of forcing these little micelles, these little bubbles within the soap.
And the ionic ends are on the outside facing the water. The cleansing action of soap occurs because oil and grease are hydrophobic and can be absorbed into the hydrophobic centers of soap micelles and washed away.
Okay, so since the oil is nonpolar, the nonpolar ends stick in and they grab onto it, where the polar ends stay in the water, and then you can pull it out of your fabrics or your clothes. Same idea here, this one just has a little bit better graphics.
Surfactant molecules exist in aqueous solution as micelles, clusters of surfactant molecules. The long nonpolar chains of the surfactant molecules are pointed inward, and the polar charged end groups point outward into the water. In solution, water molecules interact with the polar negatively charged ends of the surfactant molecules and with the sodium cations that provide charge balance. When a microscopic oil particle on an item of clothing is exposed to this solution and there is agitation, the surfactant molecules become embedded in the oil droplet through the hydrophobic, oil-loving hydrocarbon chain part of the molecules. As more and more surfactant molecules become embedded in the oil droplet, it is lifted from the surface of the clothing. This process occurs because the polar, charged ends of the surfactant molecules interact strongly with the surrounding water.
Alright, so same information, just kind of more of a 3D look at the same process. Now emulsifiers will do the same thing, but emulsifiers tend to bind like your fatty type of parts of food to your waters and other things within those kind of foods. Okay, we're going to stop here, and then we'll do our next video segment coming up next. Thanks.